Hello and welcome to my YouTube channel Electrical Hub. Here we are going to discuss about the rotor earth fall protection. In the generator protection series, we have already discussed about the dead machine protection, stator earth fault 95% and 100% protection, generator low forward power protection, and the generator reverse power protection. If you are interested to know about that, you can go and check the link in the description box. The topics we are going to discuss here are about the static excitation system, principle of rotor earthwork protection, somehow the zone of rotor earthwork protection, the square wave injection principle, how the rotor earthfall works on the basis of square wave injection principle, and also a little about the impact of rotor earthfall protection. The square wave injection principle is very important because the whole of the rotor earthfall protection system is based on the square wave injection principle. Here, we will discuss only the basics of static excitation system. The whole of the excitation system we will discuss in other videos. So, in the basics of excitation system, after the generation of the voltage is tapped off by IBD tap off to the excitation transformer. In the excitation transformer, the voltage is lowered to the lower AC voltage, which is fed to the converter. That from the converter, it is converted to the DC voltage, where it is tapped off to the AVR, and also via FCV through slip ring. It will be fed to the rotor field windings, and through which the entire induction process will happen. FCB, there is a field circuit breaker. As you can see in the drawing, that after the converter there is an FCB. So, what is the function of this is FCB? It will supply the DC voltage to the rotor winding during the normal operation. And if there is any problem or if there is any tripping, then this FCV breaker will open and it will not allow the DC voltage to pass to the rotor winding. So this FCB will either, if closed, the DC voltage will be supplied to the rotor winding, and if open, the DC voltage will not pass to the rotor winding. The next part come is slip ring and brushes. So slip rings are positive and negative. They are rotating at the synchronous speed and they supply the DC voltage to the rotor wire. While the brushes connected here are static and are not rotating at synchronous speed. What will happen if there is a rotor earth fault? There can be two cases. First, if there is any fault in the DC bus, then the current will follow the shortest path and it will go to the ground through the brushes. So the current will not reach to the rotor field and it will not create a magnetic field and the equipment will trip. But if there is a fault in the rotor winding itself, then a huge mechanical force can be created which may damage the rotor winding. That is why we need to trip the equipment to protect from heavy loss of the costly equipment like alternator and the rotor through the rotor earth fault protection. So the rotor earth fault protection become very important. Now you came to know that if there is any fault in the DC bus, the slip ring, the brushes or the rotor field winding, then the rotor will trip on the earth fault protection. So what is the zone of protection? The zone of protection of the rotor earth fault is after the FCV, the DC burst, the slip rings, the brushes, and the rotor field. It will protect only this part of the equipment. Any fault occurring beyond this, at such like before FCB in the converter section or the excitation transformer section, then the rotor will not trip on the rotor or full protection. It may trip on some other protection, but it will not trip on the rotor or full protection. Thus, the zone of the protection of the rotor earth fault is after the FCB, the DC pulls, the slip rings, the brushes, and the rotor field winding. There are three basic components of the rotor earth fault protection. First is the protection relay. In the protection relay, there are two inputs. One is the control voltage, and the second is the measured voltage, or we can say measured current IG. The second part is the injection. In the injection, we feed low frequency square waves of magnitude 50 volt and the frequency from 1 to 4 hertz. Now, this square wave is fed through this series resistor. Why through this series resistor? Because it will filter the low frequency AC voltage and is also important in the KVL calculation. During normal operation, there will be no current flowing through the IG, so that will be zero. But if a fault occurs, then there will be some current flowing through the RE, and that will be sensed by the in the circuit, and some current will flow also through the IG, which will be measured in the form of the voltage because some resistance is there. So the voltage will be sensed, and that measured voltage will be sensed by the protection relay. But in the normal operation, whatever the current is injected are completely capacitive. So there will be no current flowing through the RE or IG, it will be equal to zero. It will be completely capacitive. Due to capacitance, the leakage current will be compensated. From the measured voltage UM, it will calculate the insulation resistance, and if it is lower than the setting, it will trip. Now the question comes, why the low frequency AC voltage? Because if we will inject the higher frequency AC voltage, it will get superimposed and it will not be completely capacitive, and the rotor earthward relay will sense the fault and it will get tripped. So we inject the low frequency AC voltage of 1 to 4 Hz of 50 volt magnitude so that the current should be completely capacitive and the frequency does not get overimposed. During the normal operation, the low frequency AC voltage it follows a proper cycle of square waves. So the current becomes zero at the end of each of the cycle. But during the fault condition, the things get changed. During the fault condition, there is a shift in the rotor fault current and the Ig1 plus Ig2 is not equal to 0. It becomes greater than 0. If you will put everything in the KVL calculation, then 2UG will be equal to 2IC to RS by 2 plus RE. That RE is the insulation resistance. So, according to the value set in the insulation resistance, for example, it's 5 kilo ohm or 1 kilo ohm or 1 mega ohm, it will trip. If it will sense a value lower than that, the alternator will trip on the rotor earth for protection. Thank you. Please like, share, and subscribe. Please share it to friends. Thank you. Take care.